But I will try to show you some interesting ideas that from game theory, from control systems that can be applied in transportation systems. So I will talk first about detection in adversarial environments. We all know that sensors are very important everywhere, and especially in transportation systems. And then I will talk about complex networks and autonomy. So I have multi-agent systems. Let's say I have a lot of vehicles that communicate between each other. They communicate to the road, etc., etc., etc. And I have some attackers. That the attackers, they attack the GPS, etc., etc., etc. But I want all of them to follow the leader, even if the attacker is attacking the measurements. And then I will conclude and talk about future work. So I hope I'm brief because I don't want to hold you from lunch. So, okay, so most of this project was part of a MURI project. The lead institution is UCSB. The other participants are Berkeley and Georgia Tech. So our work is basically to analyze attackers and predict future actions. And also, we have to integrate and do some data analysis and integrate them to visualization and also to the allosphere, which allosphere is in UCSB. It's a very good facility. And if you guys are visitors, I think you can go there and see it. It's very interesting. And if you need access, let me know. I can give you access. OK, so what is the motivation behind this work? So we have different kinds of sensors, and the sensors are everywhere. So as you can see, they're everywhere. You can see a picture here of some intelligent transportation systems. Of course, in order to communicate vehicle to vehicles, vehicle to infrastructure, vehicle to road, of course, we need some sensors again here, et cetera, et cetera, et cetera. So of course, we have measurement sensors that determine the absence or the presence of a vehicle, computational sensors, monitoring, traffic, environment, et cetera, et cetera, et cetera. OK, and when I was preparing this talk, I found some interesting articles, which was this January 2015. And because vehicles, they have too many sensors, and they also have some integrated and technology which integrates all these sensors, and they communicate with a computer. So of course, they're very vulnerable to attacks. And then University of Virginia has showed why cyber attacks can happen in autonomous ground vehicles, because there are a bunch of sensors. As you can see here, we all know ABS, GPS, et cetera, et cetera, et cetera. So these are all sensors that can be attacked. So because we have to protect the sensors, we have to use some ideas from game theory, so we can be robust and also have our best response towards the worst response of the attack. OK, so this is in collaboration with my colleagues from UCSB. So these three people are professors in computer science, and this guy is the chair of electrical engineering department. And so let's see what happens. So we have a bunch of sensors. So we all know that if the sensors are deterministic, then of course we know the correct answers if less than half of them are manipulated. OK? In stochastic sensors, then we do hypothesis testing, and then the correct answer is based on a probability. Of course, we can have stochastic sensors, but we also with attacks. So this was an open problem, and this is the problem that we'll consider. So we will have stochastic sensors and adversarial manipulation. What I mean by adversarial manipulation, so the adversary will put the correct or the wrong value. So this is the trick. So he tries to confuse us. Okay, so because we have stochastic errors, so sometimes we will have the wrong answer, the correct answer. But then the adversary will try to put the correct answer, or sometimes it depends. So we will have a multitude of sensors, which, you know, if we have more than one sensor, then we have better information, and then we know what's happening. And we will try to address this problem. So let's see, let's take a very simple problem, and we try to estimate a binary random variable. Okay, so if an event is there or not, okay, 0 or 1, let's say. And to simplify our life, we will just take that both of these events, they happen with equal probability. Okay, so we have, as I said, we have n sensors, and of course, because we have error probability, we have stochastic errors, then these sensors will give us some noisy measurements. And so the correct value is x, and yi is the value reported by every sensor. Okay, so the probability of error is given by this. So if they're different and if they're the same, we have one much probability of error. Okay, but we have some attacks. Okay, so the attacks occur in m sensors, which of course m are less than n. And so now our estimation will not happen to yi, as we saw here, but to another guy, which we call it zi, which are the potentially manipulated sensors. And of course, we don't know which sensors are attacked, and we don't know anything. And of course, since we're not being attacked every time, we will have a probability of attack, which will, in our formulas, you will see that everything will be mostly independent by this probability because we don't know that a priori. Okay, so we will formulate this as a zero-sum game where the detector, which is the defender, we will try to estimate our variable x based on a multitude of sensor readings, which are the value z. So it will be a zero-sum game. So the defender will be the minimizer, and the attacker will be the maximizer. So we will, it's a minimax game. We have to find the saddle point, et cetera, et cetera, et cetera. But this is a huge a huge game, I'm sorry. So the attacker can have 2 to the power of 2 to n different possible estimators. This is the defender, I'm sorry. And the attacker can have 2 to the power of m and all square. And of course, this is only if we include possible attacks. If we include which sensors to be attacked, then it's getting even bigger. So this is a very tricky problem to handle because it's growing exponentially. But we can find some ways to find a closed-form solution by considering some bounds on the probability of error, probability of attack. Okay, so of course we can find also some other symmetries to reduce the size of the game. And so you can see that the defender can handle zeros and 1 in the same way. So for example, if I have 4 zeros, then I know that this will be dual to 4 1s. Okay, so these are dual events. So then, and also the attacker, which sensors to be attacked, of course, can be said with equal probability. And now I can reduce my game to 2 to the power of n plus 1, m plus 1 to the power squared. So again, this is a very huge game. So we will have one row for each detector and one column for each attacker. But again, this is a very big game. We can't really find the closed-form solution, so we have to find some other ways. Okay, so we have found a theorem. So for a specific probability of attack and for a small number of sensors, which is n less than 2 over the probability of error for every sensor. So then, and for this probability of attack, then we can find a way to find a closed-form solution and then reduce the game to a 2-by-2 matrix. So 2 policies for the estimator and 2 policies for the attacker, as you will see in the next slide. And the probability which we will construct these policies will be, so let's say that the probability of attack is 0, then we consider a classic estimation problem, as we all know. But then if this is not 0, then the probability grows linearly with p attack and exponentially with the number of sensors attacked. So now let's see what's happening. For this probability of attack, then we can find 2 policies for the detector, which we will call it majority and no consensus rule. So most of the times, the detector will play the majority rule. So it's like a voting protocol. And some...
You're assuming identical sensors.
Yes. Now they're identical. Yeah. You're right. Yeah, that's a good observation. Yeah. So to make everything, we have the result for also non-identical sensors, but the formulas are more messy, so I didn't want to scare you. Okay. So we go with a majority most of the times, but we have one more policy, which is, we call it no consensus. And this policy is when the detector sees everything the same, then either there was no attack, which we go with the majority, either there was attack and the attacker changed M sensors, so N minus M were the correct ones. So then we go with the opposite rule, and then we call it this no consensus rule, okay? And as you can see, the P attack doesn't appear on any of these policies. So this was our defender. And remember, this for this closed form solution for this specific probability of attack, okay? And the optimal attacker's policy has two policies, the deception or the no deception. So the deception, because the attacker knows the correct value. He knows X. So the deception, if X is equal to 0, he will manipulate it such that the defender will likely to report 1. And then the no deception is the opposite, because I remember the attacker wants to confuse us, and sometimes he puts the correct value. Okay. But as you remember, this is true only for sensors that they are less than 2 over probability of error, and so a specific probability of attack. So we want something that can do better than that. So, and here you can see some illustrations of maximum value of P attack for 11 sensors. So this is just some plots of the previous bounds that I saw you for the probability of error and probability of attack. There's not a lot to see here. But now I will show you something more interesting. You remember before we had the problem of an upper bound on the probability of attack. So now we have to define something more general. So now we have another theorem that says that for every probability of attack, again, we can find a closed form solution that's again threshold-like rule, which again, it's a voting protocol. But now our Z star is given by this guy over here. And now, before we were exactly at the saddle point of the zero-sum game solution, now we will be epsilon far from the saddle point. And this epsilon is given by this guy over here. And again, you can see that nothing depends on probability of attack. And these are specific bounds of being fooled by the attacker, okay? But again, we have another problem here. So you know, here, this gets small if we have enough sensors, okay? So if n grows, then this becomes small. So then we're closer to the saddle point solution. But let's see what happens if we have general, this is again approximate saddle point, so we're far from saddle point epsilon. And then let's make it even more general. So now, instead of, we want to estimate a variable where a Z is given by 2 distributions, R and S, okay? So now instead of just variables, we have distributions. So what the attacker does, the attacker just selects a distribution and tries to confuse us. And again, we have, some game theory design that we want to compensate for that. And I don't want to bore you more than that. Again, at the end, we can find a threshold-like rule. Again, voting protocol. And this is for general case, general distributions. We have extended to continuous time distributions, to discrete time distributions. They can be Gaussian, anything you want. And still, we can find a closed form solution. Okay, so now I will change gears, and then I will go to connected vehicles and see how the vehicles will follow the leader even in the presence of an attacker that attacks the GPS measurements. Okay, so before I talked about the sensors, now I will go in more in dynamics and try to find to use some reinforcement learning ideas such that I compensate for the attacks and also I compensate for the unknown dynamics. I know because, especially in transportation systems, modeling is very difficult, so our algorithm will be mostly model-free. Okay, so what's the motivation? Of course, I saw other talks here. They talked about machine learning. So in this part of the talk, I will combine learning and optimization. And this comes together with approximate dynamic programming. And you know, dynamic programming is a very difficult problem to solve due to the courses of dimensionality. And it's an offline procedure. But the approximate dynamic programming is online and solves forward in time. And we can solve very big problems just by plug-and-play algorithms, not by waiting in the computer for 5 hours or 5 days to compute the policies. OK, and also, as I said, because I want the vehicles to communicate and exchange only local information, of course, I use ideas from consensus algorithms, team decision theory, et cetera, et cetera, et cetera. And this is our interest here. OK, so there are some other ideas here. For example, in autonomous vehicles, we foresee that there will be a lot of intelligence there. So because the vehicles, they need to operate under unforeseen circumstances, including damage, we have to learn from mistakes, interact with each other in an intelligent way, and of course, it's impossible to pre-program behaviors most of the time. And this intelligence will bring a significant impact in many applications. OK, and OK, there's some other stuff. OK, and of course, we want our algorithm to self-heal, resist attacks, and allow dynamic optimization, adapt to unknown failures, damages, and the dynamics. And as I said before, dynamic programming versus approximate dynamic programming. And we will use this guy over here, where the system are the model dynamics. So based on the unmodeled dynamics, I evaluate how good my control was, and then I update my control. And then at the end, you will see that I converge to the optimal solution. OK, so now let's extend that to complex network. Complex networks are everywhere. You can have mixed human and man teams, several UAVs, UGVs, leaders. Also, these are some intelligent transportation systems, and these are some sensors with intelligent transportation systems. But again, modeling is very difficult because these systems are highly nonlinear, and they're very uncertain. OK, so we have to develop plug-and-play algorithms that they can yield global behavior with local interactions. OK. And so this is another, a lot of sensors that they're very, they're present in industrial transportation systems. And so our algorithm has to have a built-in attack and awareness capabilities. And also, we have to consider what is the impact of this type of automated optimization process. OK, so now, since there's a lot of interaction between car, infrastructure, vehicle, road, et cetera, et cetera, et cetera, and then we can model everything with a graph. And let's say for simplicity, let's assume that we have these dynamics. OK, you will see that the model will be independent from the dynamics. But I want you to see here that the attacker can change everything here, A, B, D, and also adds another input in the system. OK? So this input can change your GPS signals, can change anything you want. As long as the system is controllable, so then we can devise some algorithms. So, and also, of course, the algorithm will be independent of the configuration. So again, I will use ideas from game theory. So I will define my performance to be this guy here. So it will be distributed performance. So every autonomous vehicle here, it will have his own performance. And it will depend on information that he gets from his neighborhood. So as you can see, I want to minimize the error between me and my neighborhood. So I'm going to communicate with my other cars, and then I want to take their measurements. And then based on that, I will take my next action. And I want to minimize my actions, and then I want to maximize, because I have this minus sign, with respect to the attacker. So again, it's a mini-max game. And we need to find the policies. OK, so this is just the Bellman equation that solves the dynamic programming. But again, as you can see here, this Bellman equation has the dynamics inside A, B, and D. But we don't want that. And of course, the policies also have the dynamics there. So we don't want that. So you will see in the next slide that we will devise algorithms without anything from the dynamics. And of course, we have proofs for everything. And so in order to define model-free algorithms, we will use machine learning ideas, and especially Q-learning. And as you can see, in continuous time that most of the dynamics evolve, there are no known algorithms. So we have to actually convert the famous Watkins algorithm, the Q-learning algorithm, to continuous time. But the conversion is not really straightforward. So as you can see, I mean, the optimal value function to solve dynamic programming is quadratic in E. But then if we add a 0 term, which is like the Hamilton-Jacobi-Bellman equation that arises in dynamic programming, then you can see that we can find the optimal Q function. And then, as you can see, the Q function will be dependent only on the state and the control and the actions. So if we find this guy over here, then we know that we have solved the problem. But how easy is to find this guy over there? And of course, nothing depends on ABD and the graph structure. OK, so now if we find the stationarity condition in this dynamic programming problem, then as you can see, everything will depend on some submatrices of Q, and they will be model-free, and then you can compare it to the previous guys here. So as you can see, there is no dynamics anywhere, but you can compare it to the previous one where the dynamics were there. OK, and then we will use some neural networks to learn these dynamics and to also learn the weights that I had before. Since I know that I have to be done because you guys are hungry, and I don't want to bore you, so at the end I will show you some update laws to update and find the optimal solution without having any dynamics. So if you just plug and play these guys in every vehicle, then you can see that we can have global solution and global optimality, and all of them, they will synchronize to the leader. And then, oops, OK. And then let's say I have these 10 agents here, and I want all of them to follow the leader. Well, the leader is my green, so my leader does a circle. So as you can see, without knowing anything about the dynamics, without knowing anything about where my neighbors are, I can still follow the leader. And of course, this has been published in some journals. And finally, to conclude, so what I talked about is I brought together some different areas from optimization, adaptive control, game theory, reinforcement learning, network security. I found closed-form solutions for the adversarial detection problem. And I defined model-free optimization algorithms that self-heal, resist attacks, and self-optimize. And they only require local information, and of course, are very easy to implement. And some future ideas. Of course, there is a lot of work to be done in complex networks, especially for defining adaptive and model-free optimization algorithms. I know we have recently submitted a proposal to Air Force about that. Of course, security in cyber-physical systems is another hot topic in power systems, air traffic systems, transportation systems, et cetera, et cetera, et cetera. And I collaborated with some colleagues from US Army, and they want to apply some of these algorithms to their fleet of UGVs, and to find algorithms that they are fully autonomous. And this is some future infrastructure for vehicles. As you can see, the GPS signals, inter-vehicle communication, electric vehicle, road vehicle communication. And with that, I would like to thank you, and I will take any questions. I hope I didn't bore you. Sure.
I have some questions. I may have missed some of the content.
Sure.
Because things went fast. Hello. Okay. Why did you model the first work as a zero-sum game? Why? Like like the very early.
So you mean adversarial detection, right?
Yes. Okay. So why zero-sum?
Because, I mean, the defender, either you detect it or not detect it. So it's I win, you lose.
Mm-hmm.
So I win, the defender, the attacker loses. Okay. So it's a zero-sum game. There is no non-zero. You know, I mean, the one wins because I found the correct event, and the other loses. There is no non-zero-sum game there involved. So what I did is I minimized this guy, the detector minimizes the probability of estimation error, and the attacker wants to maximize that. So, yeah.
Secondly, you're looking for saddle points.
Yes.
Saddle point is the equilibrium of the game, I may infer.
Yeah.
Okay.
This is the saddle point, this is the equilibrium point.
And this is a nice equilibrium. Which concept is it? It's a nice.
This is zero-sum game, saddle point as equilibrium. Yeah.
Okay, perfect. And thirdly, you have mentioned that your approximation dynamic programming is online.
Yeah.
This means that doesn't work in rolling horizon doesn't work on rolling horizon. It's fully online.
Yes. It's if in horizon, so you just plug and play it, and then it's fully online.
Okay.
There's no offline computations, just plug and play. And so everything happens in real time, everything happens forward in time.
Okay, good. So we talk later.
Sure, yeah.
All right, thank you very much. Rick wants to stop us.
Sure.
No, wait. This is a real quick question. Sure. Have you considered for these kinds of events how many sensors you'd really need? Rather than, I take it you have a deployed set of sensors, right? And you're determining whether there's an attack or not. So, what do we need? What's the minimum number of sensors, or for various kinds of attacks?
That's a good question. So the thing is that our algorithm is general. So the thing is that we assume that half of the measurements, at most half of the sensors have been attacked. Okay? So you also have this probability of error. So you can consider those also as attacked because they give you the wrong value. So I mean, at the end, you can have half of let's say you have 3 sensors. So one is attacked because we do tie breaking, and one is attacked. But also, let's say that your other 2, they give you false measurement, false event detection. So again, you consider all of them to be attacked. And in different applications, I mean, it depends. Let's say that you want to do weather forecasting if tomorrow will rain. I don't have an exact number to give you for all these applications, but we have shown that for weather forecasting, more than 3, they're enough also. So in most of the applications that they're there, we have more than 3 all the time. I mean, 1 or 2, there's nothing. So more than 3 is always the case.